Hi there, Mathemaniacs. We are doing integration by parts. We're going to learn where it comes from and where to use it, and understand how to manipulate functions and expressions so that we can be successful with it. So this is the first of two videos. This video will give the background and 4 examples, increasing in complexity as we go, and the next video will look at some special cases. Okay, so you know the product rule for differentiation is when we've got two functions, let's say u of x and v of x multiplied together. And you know that if we want to find the derivative of that product, we have to use the product rule. We can see the product rule there on the second line. So u dv dx plus v du dx, or the same thing in different notation. And you'd be familiar with that, otherwise you're not watching the right video. So what happens if we integrate both sides? Alright, so if we integrate both sides, we have the integral of the derivative. Sounds contradictory because in a sense it is. So we find the integral of both sides. We proceed like this. And what do we get? Well, on the left side of the equals, the integral of the derivative. Oh no, stop, I forgot to put my differentials on the end. Naughty, naughty. There should be dx on the end. Oh, that's not great form. There you go. It doesn't look very good now, does it? Anyway, back to what I was saying. On the left hand side, we've got the integral of the derivative of uv. Well, that just leaves uv, which is that u of x times v of x from up there, slightly bending the notation. And then we've got on the right hand side, no changes on the right hand side. Any plus c's I'm going to leave till later too, as in demonstrating them in the questions. Okay, you could talk about arbitrary constants. We'll talk about that later when we look at some actual examples. And so if we rearrange that, and so that we've got the first term on the right hand side, u plus dv dx dx. If we make that the subject of that equation there, we've got then uv less the integral of v du dx. Now that essentially is the rule for integration by parts. Okay, so u dv dx equals uv minus the integral of v du dx dx. Okay, now that is not just a set and forget, that needs to be explained and elaborated on, so let's do that. We use this monstrosity. In fact, how dare you call it a monstrosity? It's not. You might be asking, when do we use it? Well, we use it when we've got a product of two functions, and one is easy to differentiate and the other one is easy to integrate. And so it's a case of where this part here is easy to integrate than this part here. So it assists you in the process of integration if this process is easier than this process, or if this process here is possible and this process here for you is impossible. It's a good strategy to use. One of the goals in this is how you set it up. You need to set one of the functions as u, or u of x, and as you can see, what happens to u of x, it's got to be differentiated to become du dx, and we also need to identify something else as dv dx, And what happens to it? It becomes integrated. So setting it up the right way is very important. Now, consider integral of x cos x dx. I'm going to show you what happens if you don't set it up right. It's not the end of the world actually, but maybe you can learn through this deliberate error what can happen, and maybe sometimes there's cues for setting it up right, or setting it up in a way that's better, superior. Okay, so you can see that we've got, as I said, we've got to set up u and we've got to set up dv dx. So you've got a choice here, x or cos x for each of these. So we need to set up one as u. Let's just say cos x. Okay. Well, I've seen trig functions before. Let's try that. Let u equal cos x and let dv dx equal x. Okay, so they're both accounted for now. And the order at which they're presented is irrelevant too. So we now, looking at the function, the formula, the rule, we need to find du dx as part of it. So let's go and do that there. So the derivative of cos x is negative sine x. And we have to integrate dv dx to get v, and that's x squared over 2. Okay, and the plus c, we deal with that later on. Okay, so we follow the rule. So it's uv, so we got u is cos x and v is x squared over 2, or half x squared. I'm going to put that bit first, half x squared, and that's times by cos x. So that's the uv part. So we've got that there. Less integral of v, which we said is a half x squared, times du dx, which is negative sine x. So what I'm going to do is put the negative out the front, which makes minusing a negative a positive, and the sine x there. Rightio. So we've got a half x squared cos x plus a half outside of the integral of x squared sine x. So dx there too. Uh-oh. What's happening here? Well, I couldn't get x cos x to get any easier. That's no easier. In fact, it might even be harder to integrate. And what will happen then is you go around in a circle. So try it the other way around. So this might happen occasionally, and the idea is just to stay cool and try the other way around. Okay, so I've set it up the other way around in the light green, and let's proceed. So we have u times v, which is x times sine x, or x sine x, minus the integral of v du dx. So that's sine x times du dx is 1, so that's just sine x. Aha, that's what we were looking for. Now, integral of sine x dx is easy. So, x sine x minus the integral of sine x, and that's negative cos x, so it's minus negative cos x or plus cos x plus c. And there's our answer, x sine x plus cos x plus c. Okay, now this one doesn't necessarily look like a product of two things, but we've done some work with inverse trig functions, but they've been the results of integration, not to integrate them themselves. So what we're actually dealing with here is 1 times inverse sine x. Okay, now the reason why we put in 1 is that we have to have a product there, so, and I'm writing it in the other notation. So I've let u equal sine x, and so du dx, inverse sine x. So we've been doing that fairly recently. So du dx is 1 over square root of 1 minus x squared from our recent work, and v is x. We don't worry about constants at this stage. So putting that into the rule for parts gives that, and now we need to look at what do we do about integrating that. Is it another case like above where, we set it up wrong, or not? Well, actually, if we make another sort of substitution, if we make w equal to 1 on x squared, it'll actually give us a way forward. So, no, we don't have to start again. So we're going to use integration by substitution now, so we need to know what, normally this would be called a u substitution, but I'm using the symbol w here. dw dx equals negative 2x. Now, what we've got here is that I'm going to move deliberately the x, and I'm going to do that live. I'm going to move that there so we can explicitly see what's going on. Select blue. Okay. That x now is there. That's got to be a 1 there. Just so we can see what's happening. Now, over here, dw equals negative 2x dx. To get the x dx that we have over there, it's negative a half of dw is the equivalent. So we've got the x dx, and that can be replaced by negative a half dw. So we're going to put the negative a half in there. There's the half. And the negative will actually turn that into a plus. So plus a half integral. It's time to make that substitution now. So we've got our dw there, and we can put in dw, and we've made the substitution involving w there. Now, some people might not like that I've got two variables happening there at once, but a lot of people don't mind you. So we've got everything in check there. I might now change the 1 over root w into index form. So that's w to the negative a half dw, which is easier to see what to do with the integration. Now we add 1 to the power, and we get w to the half over a half plus c. We've got x sine x. Now we've got a half divided by a half. That just leaves the w to the half, or root w plus c x sine x. Substitute it back in now. We had a substitution earlier that w equals 1 minus x squared, so we sub that back in now. Plus c. Oh, how embarrassing. Did you notice that I dropped my notation all the way through? I hope I didn't confuse anybody. That's uv there, isn't it? Okay, or in fact uv was the other way around. That's u, and that's v. So that should be inverses. Sorry. There's our answer. Okay, so when you've got definite integrals, so we've just done some antiderivatives there, now some definite integrals by parts, What do we do when we're asked to find something like this? Do we panic, crack each other's skulls open and feast on the goo inside? Well, no. It's pretty easy really. It can be shown that this is the case here. We simply just put the same limits on each part. There's no calculus in that part there. And so we have between B and A, we simply just put the limits of integration on there for our definite integrals. Let's do an example of one. Okay, so I've started the next one off. So it's the integral of log x between 2 and 1. Okay, so set u equal to log x, because log x is quite easy to differentiate by now. Integration of it's different matter. So natural log x equals u. dv dx equals 1, because that's easy to integrate, but if we try and differentiate 1, by the way, there is a 1 there, like we saw previously on a different question. Okay, if we try and differentiate 1, we get 0, so no. So that works. Okay, so integral is x, and the derivative is 1 on x. So let's play ball. So u times v is log x times x, or we'll write x log x, minus between 2 and 1, the integral of v's, which is x, and times du dx, which is 1 on x. Oh, that looks good. We're going to be able to do things with that. And scroll down. We've got easy to evaluate here. We have 2 log 2 minus 1 log 1, and log of 1, 0. Now I'll put braces around that so we don't worry about subtracting negatives and all that sort of stuff. Okay, now x times 1 on x is just 1. So it's the integral of 1, which is x. So that'll be x between 2 and 1. Okay, so that's just 2 log 2. Now that'll be 2 take 1, which is 1. So it's 2 log 2 take 1. One more to go. Now occasionally you'll get one that won't let go without a bit of a fight. So for persistent ones, let's see an example. This is not a terrifically difficult one. We got integral of x squared multiplied by e to the x dx. I've started off, let u equal x squared, so du dx would be 2x, and dv dx equals e to the x, so v equals e to the x, ignoring the constant for now. So we plug that in, we got u times v, which is x squared e to the x, minus, this is an antiderivative, it's an indefinite integral, so there's no limits on this one, and we've got v times du dx, which is 2x times e to the x. I'll write it in that order. Dx. Okay. Now, once we get to this stage here, we might have thought, oh, have we set it up wrong? Or will it go with one more round? Well, we have to think about that. So you could go back and think, maybe could I have set it up differently there? But if not, have a look, is it improving? That's the thing, is this improving? I reckon so, because every time we take the derivative of that first term, it gets closer to being a constant, and then a constant can move out the front, and then we'll just have e to the x by itself. Do you understand what I mean? See, it's all about strategy. So, we have that one. So what we have to do is go through the parts process again. Alright, so I'm going to call, it's very thematic part, the word part is all through this. So part 2, we're going to set this up I've just called it part 2 because I'm going to use these same symbols here instead of introducing alphabet soup. So if we let u equal x, du dx would be 1. Ha! And that's a very good sign. And dv dx, the thing that has to be integrated, would be e to the x. So v is e to the x, good old e to the x. I am my own grandpa. So we have x squared e to the x, and some beautiful algebra coming up here, minus 2 outside of, we have double brackets. Alright, pulling out the big weapons here, we need u times v, which is x e to the x minus the integral of v du dx, which is e to the x times 1, which is just good old e to the x. I am my own grandpa. So it keeps going down through the lineage. So x squared e to the x, close the door. Okay. So it's minus 2 x e to the x. Yeah, that's just e to the x. I'm going to put plus c out in the cold. And we got x squared e to the x minus, so what we got in here is we got 2x e to the x minus 2 e to the x plus c. We've got x squared e to the x. Now be careful, minusing, that first term will be a negative and the second term will be a positive. Okay, so we've got minus 2x e to the x, and it's plus 2 e to the x plus c, you see? And we can take a factor of e to the x outside of that. Alright, especially if we do that. Alright, and so we got e to the x outside of x squared. X's are having a bit of a tantrum on me tonight. X squared minus 2x plus 2 plus c. Thank you very much.